So today, sir will be joining online only, and now we will be playing the hardware demonstration setup, and you will be able to see that. If you have any questions, please note it down. Whenever sir will be available with us, then we will be, having discussion over that. And the video link we will be sharing you again on the canvas, and also the related PDF we will be sharing you on the canvas, so you can go through those videos and slides on the canvas. And for any discussion, we will quickly have one day and we'll discuss it. So now we are going to start the demonstration part. Thank you. Wait, we are again publishing the screen.
Dear student friends, today we are going to discuss on demonstration of wind power generation of the course titled Smart Grid. Basics to Advanced Technologies. Now we are going to discuss on a test bed for the demonstration of wind power generation, and as you could see, this is the brief introduction to wind power generation. Ideally, we capture the kinetic energy through wind turbines and through gearbox to the generator and through power converter to the transformer, and hence the energy is being fed to the power grid. A typical wind power generation convert kinetic energy of the wind to the useful electrical energy. The aerodynamic modeling equations of the wind turbine helps to assess the performance of the wind turbine with respect to the varying wind speed. The power generated from the wind turbine is a function of the power coefficient and the wind speed. With the recent development in the semiconductor technology in the field of wind energy, the less productive fixed type wind generators are being replaced by the partially variable and completely variable types. Among the variable type of generators, the DFIG wind system, which is one of the partial variable type, is known for its cost effectiveness due to the scale down in the converter size. The power converters are rated to handle complete range of wind speed variations. Now focusing on doubly fed induction generator, so called as DFIG WPG, the schematic representation of the DFIG wind system along with the power flow is shown in this slide. As the name suggests, the doubly fed induction generator is capable of feeding or observing power in two directions. The stator part is directly exposed to the grid, which works at fixed voltage and frequency. Henceforth, it is mandatory that the stator of the DFIG is compelled to operate as per the grid norms. However, this is only possible if the rotor operates at synchronous speed. In a practical scenario, the speed of the generator keeps on varying from the sub-synchronous speed, say in the morning hours when the wind speed is low, to the super synchronous speed in night hours when wind speed is extensively high. Thus, with the conventional induction machine, it is not possible to inject power from the wind system to the grid. With the DFIG setup, it is possible to inject power at varied wind speed into the grid via stator over a speed range of plus or minus 30%. During the subsynchronous mode of operation, since the wind speed is less, the positive slip power is drawn from the grid via rotor side converter, grid side converter, combination to the rotor, such that the prescribed power at the grid frequency could be injected from the stator end. By neglecting the losses of the back to back converters, where Pg equal to Pr, we can say that the power at PCC is equal to the addition of the power generated by the wind turbine, that is the stator power and the rotor power. Here P equal to Ps plus Pg, that is the summation of Ps and Pg. During the subsynchronous mode of operation, rotor speed is less than synchronous speed and thus the slip is positive. Similarly, during the supersynchronous operation, the excess power from the rotor in terms of negative slip, power flow out from the rotor via RSC and GSC combination, thereby helping to follow the grid norms as per the nominal values. Whereas during the synchronous mode of operation, there is no power injected or absorbed from the rotor and the entire power flow from the wind system is transferred to the grid via stator itself. In summary, by controlling the RSC and GSC, the DFIG wind system can be made to function in all the three modes of operation. Now, focusing on the hardware demonstration of the setup of wind turbine, grid connected operation of the DFIG setup. Now, before going into the demonstration, let us have a look at the overall hardware connections. DFIG hardware setup consists of three units mainly. The first one is a wind emulator, DFIG, and back to back voltage source converter. The laboratory setup of DFIG is basically a slip ring induction machine coupled with DC motor. This DC motor of rating 2.5 kilowatt, 220 volt, 10 ampere, which behaves similar to prime mover and is controlled by chopper control, providing different wind characteristics. For obtaining the wind emulator, the wind characteristics along with the wind turbine action is mimicked with the help of a buck converter. The DC motor output is controlled via armature voltage control, for which the semicron IGBT stack is being used. An inductor and a capacitor is used to form the buck converter. The control strategy for buck converter is as shown in the schematic diagram. Now, the DFIG control, so called wind emulator, it can be noticed that the wind power, which is half of rho A Cp V cube, in the control scheme is calculated by taking input wind velocity and pitch angle. Here the Cp is the power coefficient which is dependent on the pitch angle and tip speed ratio. Further, the wind power is divided with the measured speed of the rotor to generate the reference torque. The motor reference current is obtained by multiplying the torque reference with the motor constant of value K, which is equal to 4.16 in our case. The current reference is then compared with the actual current of the DC motor. The compared result is sent to the PI controller, thereby obtaining the switching pulses. Now, the induction generator of 2.2 kilowatt rated and is operated through the field programmable gate array FPGA based controller. Vivect FPGA controller of firmware version WCU 10081E is used, which is capable of sensing 8 voltages and 8 current signals along with 8 PWM pulses. While the stator of the slip ring induction motor is connected to the power amplifier via a switch, the switch is initially open and is further closed when the stator voltage and phase angle is synchronized with the voltage and phase of the grid and phase angle using the rotor side converter. After synchronization, RSC regulates DFIG to operate in the speed power control mode. Rotor of slip ring induction motor is connected to the RSC, which is controlled in the FPGA platform. Now, if you look into the DFIG control through rotor side, field oriented control FOC established on the vector control is enlisted for D and Q axis control of rotor current. The maximum power point tracking MPPT is implemented using perturb and observe P&O method by estimating MPPT reference rotor speed at particular wind velocity, regulating the Q axis of the rotor current IQ RSC. Now, the D axis part of the rotor current is governed for managing the stator power factor. This is done by introducing reactive power for smooth variation. Further, the reference voltage is converted to the ABC frame to generate the PWM signals, which is fed to the RSC switches. The RSC is connected to GSC via a DC link, and the job of the GSC is to maintain the DC link voltage. Now, looking into grid side control, the generated DC link voltage when compared with the measured voltage of DC link generate error that is processed through PI controller to obtain D axis reference current. The measured GSC current D axis component tracks the reference value with the PI controller to obtain the reference D axis voltage, while the PI controller dealing with the Q axis component of GSC current is assigned to regulate reactive power injection. Now, the software which is available through Vivect suite for FPGA controller that run on HDL coder, in this platform we provide the governing variables value. First, we connect the Vivect via a LAN cable to the PC and connect the supply voltages. The supply voltage we give by power amplifier of rating 15 kilovolt ampere and 50 hertz. The 3-phase voltage is set in the amplifier 140 volt to get line to line voltage of 240 volts. The grid voltage is reflected in the software due to presence of voltage sensor at that point. The main and the rotor branch circuit breaker is switched on and the DC link is charged initially to 340 volts. Then we enable phase locked loop and check the reference theta with the phase A voltage. Once the DC link is charged, we enable the GSC control to maintain the desired DC link voltage, which is set to say 30 volt greater than DC link voltage, that is close to 380 volts. We see that GSC tracked the DC reference voltage and measured DC link voltage is read as 385 volts. Now, the next step is to enable DC motor control to run the DC motor to provide wind characteristic in the rotation. Here we vary the duty of the chopper gradually to make the motor run at more than 900 RPM. We are varying the duty and notice that speed is keep on increasing. We can check the rotation here in the speed panel. We see the DC motor is driving the induction machine. Next, we provide the PI value of the rotor side control and enable the control loop. The RSC first is used to build up voltage in the stator side and then match the phase difference of the grid to the stator till they align for the synchronization purpose. Now, we will increase the reference value to match the stator voltage magnitude with the grid voltage using the D-axis control of the rotor. In this process, we also observe that the rotor current is also increased as it takes current from the grid to build the stator voltage as from the relation the stator power is 1 by slip times the rotor power. I repeat, in this process we also observe that the rotor current is also increased as it takes current from the grid to build the stator voltage as from the relation the stator power is 1 by slip times the rotor power. The slip is varied plus or minus 30%. So, small current injected to rotor side results in a larger voltage across the stator. Then we vary the Q axis of the RSC to vary the theta. We change the reference till theta is matched. If we see the grid and stator voltage, we see the waveform almost overlap with one another. After voltage get matched in the software, then we check the contactor of the grid side and stator side and ensure that the voltage across the contactor in multimeter is less than 20 volt. Here we are getting a value of less than 10 volt across all 3 phases. By ensuring voltage is less than the contactor connecting the stator and the grid connection is closed, and then the synchronization is done by enabling sync done in the software simultaneously. Now, the control of RSC is changed from synchronization operation to power speed control mode. Here we see that the 3-phase rotor power is sent. Now, we enter the speed control mode and vary the wind speed to vary the rotor speed. Here we demonstrate the DFIG in 3 different operating modes. Number 1, subsynchronous mode, 2, synchronous mode, and 3, supersynchronous mode. Now, in case of the subsynchronous mode, the rotor angular frequency is lower than the synchronous angular frequency, where omega r is less than omega s. We consider omega s, which is close to 1000 rpm, and the slip is greater than 0. The total power to the grid is 1 minus slip times P stator. The stator delivers power to the grid while the rotor receives power from the grid. Next, we slowly increase the speed and bring it in the synchronous mode. The rotor angular frequency is equal to the synchronous angular frequency, where omega r equal to omega s and the slip which is equal to 0. DC current flows into the rotor winding. The total power to grid is P, which is stator power. Only the stator delivers power to the grid. If we further increase the speed of the DFIG, works in the super synchronous mode. The rotor angular frequency is higher than the synchronous angular frequency, that is omega r is greater than omega s, and hence the slip falls which is less than 0. The total power to the grid is P, which is 1 plus slip time P stator. Now, both the stator and the rotor deliver power to the grid. With this, we have today understood how a DFIG wind turbine operates, and thank you for your attention. Very good morning. Welcome to the course on Smart Grid, Basics to Advanced Technologies, and we are going to discuss on battery management system today. The main functions of battery management system, that is so called BMS, are monitoring the current through the circuit, cell voltages, and ambient temperature, estimation of key states such as SOC, SOH, and SOP using online estimation techniques, cell balancing to balance the voltage or SOCs using active or passive components, computing the energy and power limitation of the pack using estimated SOC and SOH values. However, in this lecture our contributions are confined to the demonstration of cell balancing techniques only. A detailed description of other functions is provided in the previous BMS lecture. Generally, the health of the lithium ion batteries will be degraded after some cycles of usage. This poses differences in their capacity and results in a decrease in their efficiency. The weak cell in the module charges and discharges faster compared to other cells. To mitigate these issues, balancing of cells are necessary, and it allows the batteries to look alike in capacities and increase the efficiency of the cells in a given module. Cell imbalance can be categorized majorly in two types. First one temporary and the second one is permanent. The temporary causes of cell imbalance include uneven distribution of leakage and self discharge currents. The difference in Coulombic efficiency, which is a minor imbalance, performance or operation, and uneven temperature distribution. Assuming that all the cells have the same composition, the Coulombic efficiency, performance or operation, and self discharge will be the same, leaving the most significant imbalance factor, uneven temperature distribution and leakage currents, current distributed to the BMS. The permanent causes of cell imbalance include internal resistance change, self discharge rate, damage to static electrolyte interface, and capacity differences. If this continues, the weak capacity cell will gradually deteriorate prematurely than others. Imagine a case where a less capacity cell and fully capacity cell are connected to a load. It will neither discharge nor charge. A detailed discussion on the importance of requiring a balancing circuit in the BMS is provided in the theoretical lecture on the BMS, that is battery management system. Kindly refer to the lecture for more detailed information. There are many cell balancing methods. Cell balancing is broadly divided into two methods, passive and active methods. The passive methods are segmented into overcharge and shunt resistor methods. The active balancing methods are segmented into cell to cell, cell bypass, and pack to pack balancing. The basic balancing required for a module is cell to cell balancing, also called cell balancer. This cell balancing is again subdivided into adjacent cell to cell any cell to any cell and direct cell to cell balancing, let us consider the passive balancing system. This experiment aims to demonstrate a simple passive balancing for the charging and discharging operation of 3 lithium ion batteries through a readily available balancer IC. The bleeding register present in the ICs allows the charge of the higher capacity cell to deplete through this register for both charging and discharging operations. The components required for this experiment are 3 18650 lithium ion cells, a readily available passive balancer IC, a DC power supply for charging operation, a rheostat for discharging operation. Let us get into the component specifications and their importance in this experiment. 3 18650 lithium ion cells of 3000 milliampere hour capacity with a nominal voltage of 3.7 volt each are used in this experimentation. The lithium ion cells are connected in series combination to make up to 11.1 volt. The passive balancer IC with specifications as 3S 20 ampere and 12.6 volt maximum, it can handle 20 ampere of current and have protection for short circuit, overload, discharge and overcharge, which provide safety and protection for the lithium ion batteries. A DC power supply is used to charge the battery and a rheostat of 20 ohms for discharging operations. You can see the passive balancer IC. The connection diagram consists of 3 positive connections from the battery and 1 negative terminal connection, and a pair of positive and negative is provided for the external connection, which is for the charging and discharging connections. Now, the detailed architecture of passive cell balancing has been presented before you. This is the schematic of the balancer IC, which consists of 4 N channel 85N3L switching MOSFETs, DW01 overcharging and over discharging protection IC, G1 SMD NPN high voltage transistors, 2L PNP high voltage transistor, 1 port charging and discharging terminal, and few resistors and capacitors. After connecting the batteries to the balancer IC, we are going to check the balancing operation for both charging and discharging using the DC power supply and rheostat respectively. Let us observe charging operation. The battery module is charged by the DC power supply, and the path of the charging goes through the DW01 protection IC, and through that switching MOSFETs 1 and 2. Once the battery reaches its limit, the switching MOSFET activates and the current takes the resistive path until all the cells come to the same voltage. One of the ferrocell voltage or peak charge voltage 4.2 volt is reached. The protection IC activates and stop the charging operation of the battery module. Similarly, we can also see the discharging operation. In case of similar to the charging operation, the current passes through DW01 protection IC and through switching MOSFETs 3 and 4. Once the battery module reaches the cutoff voltage of 2.4 volt, the switching MOSFET activates and depletes the charge of other batteries until all the cells reach cutoff voltages. Similar to the charging operation, the DW01 activates once all the cells voltages reaches cutoff voltages. As we can see from the DC power supply display panel, we can see that 12.6 volt is appearing across the terminals of the balancer IC. With a current of 1 ampere and a wattage of 12.6 watt of power is storing in the batteries. Since the battery current takes the resistive path for balancing, heat is generated inside the module, which leads to deterioration in the battery capacity and may even cause thermal runaway. In this regard, even though passive balancing is easy to implement and has less cost comparatively, it is not recommended for large modules because of frequent failures. Moving to active balancing, in this experiment we aim to demonstrate how an active balancing mechanism works by utilizing TMS 320 F28379D as a controller and Opel RT as a plant. To perform active balancing, one should determine three major factors: mode of charge distribution, for example, direct cell to cell, adjacent cell to cell, energy sharing, balancing topology, that is type of converter, boost, buck, flyback, half bridge, and third is balancing strategy, that is what type of control logic parameters need take care of, example voltage, OCV, SOC and SOH. Now, this is what generally the CHIL setup look like, and in due course of time I will be explaining you the complete operation of CHIL setup. Now, first of all, what is a CHIL experimentation? The controller hardware in the loop system allows the verification of the proposed control logic provided in a real time controller in conjugation with the plant, which is running at a very fast time scale either in real hardware or controller. Thereby, any changes in the control logic in the real time should be governed and processed by the fast acting plant. The components required for this experiment are a TMS 320F 28379D launch pad and an Opel RT controller and a simple PC. In this experimentation, the charge distribution considered here is energy sharing and balancing topology is a boost buck converter, and the balancing strategy is based on SOC. This is the schematic of CHIL experimentation. The working of CHIL is shown in this diagram. Firstly, The TMS board is equipped with ADCs and EPWM pins. The input will be provided from the OPLRT, which is taken here as a plan to the ADC of the TMS board and is utilized for the control logic development. By utilizing MATLAB, the control logic is developed, and through hardware simulation the developed code in MATLAB is flashed into the TMS board. The necessary parameters will be called out into the console to verify the control logic for various parameters. The EPWM terminal pins present in the TMS board generates PWM pulses which are connected to the OPLRT through digital input pins provided to it to drive the converters. Let us discuss the construction of CHIL setup in the following steps. Step number 1. Consider a battery system of 3 modules, so called plant in OPLRT. Step number 2, call out the necessary parameters required for balancing strategy from the plant. Step number 3, develop a balancing code in MATLAB using the called out battery system parameters. Step number 4, do the necessary connections, that is the parameters from the OPLRT analog out pins to ADCs of the TMS board with proper scaling. The PWM pulses from TMS board EPWM pins to digital out pins of OPLRT to drive the converter sitting in the plant. Now, we can look into the complete block diagram of the battery system within OPLRT. This is the block diagram of the battery storage system connected to a DC bus, and from the diagram we can observe that the 3 battery modules connected to a load or charger, each module consists of a CMB known as cell management block, which consists of cells connected in a series parallel combination with a balancer circuit. The driving circuit, which takes input from TMS, drives the MOSFETs. Let us discuss the working principle of the battery system. The system consists of 3 modules and a boost buck converter, each to step up or step down the battery voltages as per the requirement. Such a mechanism is called energy sharing because each module can be controlled individually, which resembles the sharing of the power demand accordingly. If the duty cycle D of all the converters are same, then all the batteries share power equally. By using this concept or mechanism, we have developed a control logic that provides duty cycle D based on the variations in SOC values of the battery system. A TMS board is equipped to generate the desired PWM signals. The TMS board, which takes the input from the OPLRT currents SOCs and power demand PD, generates D1, D2, D3 duty cycles based on the algorithm flashed into the microcontroller. The parameters of the storage system are presented in the table as shown. The initial SOCs are taken as SOC 1, which is 65%, SOC 2 62%, and the SOC 3 70% respectively. The average SOC is close to 65.66. The nominal voltage for 3 modules is 48 volts. The capacity of modules is taken as 5 ampere hour each, and initial DC voltage is 270 volts. Initial power demand is 1000 watts. The converter parameters as inductance of 5000 microhenries, the capacitance of 200 microfarads with switching frequency of 5 kilohertz. This is the back panel of Opal RT, where we can see multiple groups. The group 1 consists of analog in and analog out. Group 2 consists of digital in and digital out. As we can see, for our experiment purpose, we have used 7 analog out signals with a ground pin and 3 digital in signals with a ground pin connected through a DB37 channel. After setting up the connections as per the block diagram, let us understand the simulation platform of both Opal RT and TMS board. Firstly, the required MATLAB installations for the TMS board need to be done. Also, the control suite for the C2000 microcontroller is required, which provides libraries at every stage of development and evaluation. After the installation, MATLAB provides hardware libraries for the TMS board. In this experimentation, we have taken 7 parameters as an output from Opal RT, analog out for control algorithm. The parameters are input battery currents, SOCs of 3 batteries, also the power demand PD. All the 7 parameters are scaled down to 3 volt at Opal RT itself, because the TMS board runs on 3.3 volt only. Any higher voltage might damage the board. 7 ADC blocks are taken for the 7 input parameters. 3 battery currents are compared with reference currents generated from the algorithm. The SOC balancing algorithm is developed based on the average standard deviations. By comparing the SOC values with the mean values, a balancing factor is determined for all the 3 batteries in a similar way. Using the balancing factor, the power is shared among the battery module accordingly. By using a PI controller, the voltage bus is maintained and also develops PWM signals. These 3 signals are sent to the Opal RT through digital input pins for 3 converters presented in the plant. The Opal RT plant model, which consists of 3 battery modules and 3 converters that are connected to a common DC bus with a power demand of PD. Now, let us focus on its operation. To evaluate the proposed control algorithm, experimentation using a built-in MATLAB equivalent circuit model is developed. The simulated model consists of 3 battery modules, and each module is connected to a bidirectional DC-DC boost buck converter for discharge and charge operation according to the reference current provided to it from the control algorithm. The converter consists of an inductor of 5000 microhenry and a filter capacitor of 200 microfarads. The battery nominal voltage taken here is 48 volt for each module. Now, if you focus on discharging operation, the individual battery currents is presented in the DSO at the first 3 channels and SOC values in the next 3 channels and power demand PD in the 7th channel respectively. Now, let us focus on the variations in load demand. To examine the control algorithm for load power variation, load power changes are applied to the batteries during discharging operation. Initially, the power demand is kept at 1000 watt and a gradual increase of power by 200 watt is applied till the power demand reaches 2000 watt. We can observe the input current of batteries in the first 3 channels of DSO. Also the SOC values are draining faster than the earlier. From this, we can understand that the algorithm takes the power demand changes without any setbacks. Variation in bus voltages. In general, the DC bus voltage from the energy storage should be always maintained irrespective of changes in battery voltages. Let us observe how the V bus changes are taken care by the proposed control algorithms. The initial DC bus voltage is taken as 270 volt and then it is changed to 300 volt and 260 volt respectively. It can be observed from the DSO the change in DC bus voltage does not affect the battery voltages or currents and the DC bus is perfectly regulated. Variation in SOC values. Let us change the SOC values to 75, 73 and 65 respectively compared to the previous values for all the 3 modules and observe its effect. From the DSO, we can observe that the change in SOC is proportional to the currents of the battery, which validates that the proposed algorithm is working exceptionally well to cater to all the changes. In this lecture, we have learned the 2 popular balancing techniques, that is passive and active balancing, how to develop a control logic using a low cost TMS board, understanding of how to develop and work on a CHIL setup for a balancing mechanism. I hope and confident that this lecture drives you to work and develop balancing mechanism for various topologies and balancing strategies of batteries in future. Thank you.
Okay, so today we had demonstration on 2 topics. One was the wind power generation, other was the BMS, battery management systems. So hopefully the video was very nicely, explained everything, and hopefully all of us has got many things to learn. Still, there is possibility that there may be doubts. So you can note it down, or even if you can study it later. And if any doubt, we will discuss when Sarij with us. So thank you very much. We will continue our day 17, that is tomorrow at 5 p.m. only. So thank you. Now we see off for today. Thank you.